Okay, YouTube, as we're exploring solving radical equations, it's a kind of an appropriate time to look at a model that involves, say, a radical in its equation. So let's go ahead and consider this model that we've got written right here and see what we can do with it. So it says in a hurricane, the average or the mean sustained wind velocity v, which is being measured apparently in meters per second, can be modeled by this right here. So our v, essentially what we have here is our average wind speed here being modeled by this, where P is the air pressure in millibars at the center of, say, a hurricane. So what we're looking at here in this situation is that P is our independent variable. That's our input. That's usually like what we have in as an X. And so our X value of every ordered pair on this graph is going to be our pressure. And this pressure is being measured apparently in millibars. And if we know the pressure, according to this model, what it says is I can tell you the V. And this is volume as, volume. This is velocity, wind velocity v, okay? And it is wind velocity as a function of pressure. So you tell me a pressure, and I can tell you the average wind velocity, essentially, is what this model is saying. So as we read through this here, it says estimate the air pressure at the center of the hurricane when the mean sustained wind velocity is 54.5 meters per second. I hate to say that this is a plug and chug situation, but when you look at what they gave us here, this 54.5 that is given, this is the mean sustained wind velocity. In other words, this is a v of p value. So in other words, what's happening here is that we are getting the y information, 54.5 is our wind velocity, and we're being asked to go backwards and say, well then yeah, tell me what the pressure is here. The interesting thing is, the faster the wind moves, the lower the pressure. The higher, the slower the wind moves, the higher the pressure. It's a weird situation. I won't go into it, but what I will say is this. Given our model here, if we're given v of p, 54.5, all we are really going to do is we're going to plug that in for our velocity value. We're going to work backwards to solve for the value of p, which is inside this radicand here. So with what we have, let's go ahead and plug in our 54.5, which was a wind velocity. We're going to plug it in for the wind velocity here, average wind velocity. And we're just going to solve this. Now, interesting story is we solve some radical equations. You know that we have to isolate this radical before we can do anything else, which means that the 6.3 has got to hit the road. So getting rid of this 6.3, the nice thing is on the right side we get the square root of 1013 minus p. On the left side we get 54.5 divided by 6.3, and I can't wait to show you this here. 54.5, I checked this out already. 6.3. Blech, yuck, I don't like this. This is, as a matter of fact, this is totally a rational number, which means it's decimal. It repeats indefinitely, but you can't tell with what you can see right here. So what we're going to have to do is this. We're either going to have to round this, which means everything after this is going to be thrown off, or what you're going to do is you're just going to leave this as it is. And that's the choice I'm going to make here. So I'm going to say that the left-hand side is just simply, since I can't write a nice nifty decimal on this, is just this. So the nice thing about solving radical equations is that all you do have to do is get the radical by itself, and we can exponentiate both sides to undo it. And now we've accomplished this. So now that I have both sides here, now that I have the radical isolated on the right-hand side, we will exponentiate both sides to the power of 2. And what we end up with is this. Now, you might think this doesn't look very pretty, and it doesn't. I would be the first to agree with you, but it's exact. And what I know is this. We're almost solved for the pressure here, P. We just need to isolate the P. So this means we're going to have to subtract 1013 from both sides. And so this left-hand expression here, it's going to become this. It's going to be 54.5 all over 6.3. This is, of course, squared, minus 1013. And sadly, this equals negative P. So what we're going to do is we're going to cheat a little bit here. We're going to rewrite P. And without showing all my work, I'm just going to say, well, then a positive P would have to be equal to a positive 1013 minus all of this here. This would be a negative out in front now if we were to switch its sign. So we get a 54.5 all over 6.3 squared, and this is our pressure. And as a matter of fact, I'm going to write a little note here. This is the exact value. So if we're going to get this on a calculator, and we don't want to lose accuracy, this means that we're going to wait to the last step to round. So I'm going to go ahead and type this in here. We got 1013 is what we came up with, minus now in parentheses all of this stuff here, 54.5 divided by 6.3, all of that squared. And what we end up with here is this. 938 we'll go 2 decimal place values here. 938.16. So we get the pressure is approximately 930, that's hard to read. We say the pressure is approximately 938, oh my goodness, 38.16, and we're going to label this. It is important in application situations to get your variable straight and label. So we say about 938.16 millibars. So what I want you to do is this. For this what if in number 4 here, it says estimate the air pressure. So same thing here, estimate the air pressure, P, at the center of the hurricane, but when the mean sustained wind velocity is 48.3 meters per second. So you notice that this is smaller than what we started with. And if you remember me saying this at the beginning of the video, or you love earth science, and good for you if you do, or physics, you'll know that when the wind velocity decreases, the pressure actually increases in the system. So what you're going to find is higher than 938.16 millibars when you go back and repeat this process again. Cheers.